Here's a battery. We know a battery has a positive terminal and a negative terminal. But what's inside of the battery? It turns out the positive terminal contains positive charges. And surprise, surprise, the negative terminal contains negative charges. That's not the case for most objects. Usually, and this is true even for dead batteries, normally the positives and negatives are mixed evenly. But a battery is a device that separates those charges from each other. How does it do that? Well, it finds the positives and it pushes them over to the other side. And it finds the negatives and it pushes those over. But wait, it's exerting a force over some distance? To do that requires work. Where does the battery get the energy to do this work? The answer is, it has some chemicals inside. And I like to think of them as, a large tank or something. So here is the chemical. And what happens? Well, there's chemical energy stored inside. And every time you move one of the positives over, every time you push the positive to one side, like this, you use some of the chemical energy in the process. And you keep doing this, using up the chemical energy, until eventually there's nothing left and your battery is dead. Back to the battery. Right now, the battery prevents any mixing. But the charges can't just go spilling out. That would be kind of dangerous. So they're locked in place. But if you take a light bulb and you want to get some light from your bulb, and let's say that you connect this light bulb to the battery by a wire. Well, look at what we have. Now there is a path for charges to flow through. These positives, they are repelled from each other. And finally, they can start to spill out one by one. So the charges come out, they pass through the wire, they go through the bulb shines, and they finally reach their destination. When they get to the negative terminal, though, what happens? The battery says, no, you're not allowed to hang out here. And it pushes it back over to the other side, separating the charges. As it pushes the charge back over, it uses some of its chemical energy. We can understand this process by making an analogy to a positively and negatively charged plate. As the positive charge travels around the wire and through the bulb, it's moving from the positive side to the negative side. It's losing electric potential energy. Where does that energy go? Well, we're putting a light bulb in its path. And so the energy is getting changed or converted into light. Let's make a table to summarize what we've learned so far. Another way to refer to the battery is with the word cell. The external circuit, that's everything outside of the battery. In the external circuit, charges are losing electric potential energy. Q loses PE. But inside the cell, let me get that charge. Where'd it go? Where are you, buddy? Once the charge, it's finished, it goes all the way around, it goes through the bulb, and it's done with the external circuit. It goes, now it's inside the battery, and it gets pushed back over. It just gained potential energy. It's back over here, and it wants to fall away from the other positives. So inside the battery, inside the cell, Q gains electric potential energy. What else could we say? You can't just destroy energy. That PE must go somewhere. It's converted. What is it converted into? Well, it depends. It could be converted into light if you have a light bulb, internal energy if you're working with a resistor, which heats up. Maybe it turns into your toast, right? Changes your bread to toast. inside the cell, in the battery, what's the transformation? Well, something has to create this electric PE. Where is that potential energy coming from? It comes from chemical energy. Chemical energy converts into electric potential energy. When we're drawing circuits in physics, we don't draw a battery, we draw two lines to represent the cell. And we're not going to do bulbs right now, we'll come back to those later. Let's draw a resistor. In the US, you would draw a resistor as this kind of sawtooth pattern, but in Britain and for IB, we draw a box. Remember that table on the last page? The one that said, where does the potential energy go? Resistors convert it into heat, or internal energy. Okay, the resistor has some resistance R. It opposes the charges. That's because the resistor has molecules inside. And when the charges come through, they bounce around and they kind of bump into these molecules. And so now the molecules are moving. Internal energy has been created because of the resistance. The battery has a positive terminal and a negative terminal. We make the positive terminal a long line because that's where the charges have more energy. What happens to their energy? When the charge crosses over the resistor, it loses its energy. Where is the energy going? It's turning into heat. We're not going to talk about the potential energy. We're instead going to talk more about the potential energy per coulomb. Wait, what's that called? Oh yeah, that's potential difference. Here's a question. Is this potential difference positive or negative? Well, charges are losing potential energy, so it could be considered negative. What about the battery? Is the potential difference across the battery positive or negative? Well, charges gain potential energy as they move across the battery, so that's positive. We call that positive potential difference the EMF, or the electromotive force. And for now, we'll just think of it as the battery's positive potential difference that's given to the charges as energy. One of the most important equations we'll be using is the definition of resistance. It's potential difference over current, or we like to rearrange and cross-multiply I and R. Here's a battery, and the resistance of this resistor, let's say, is 5 ohms. The EMF of the battery, the positive potential difference, is 15 volts. You can think of that as the energy given to the charges, because after all, a volt is a joule per every coulomb of charge. The question we have is this. What's the current traveling through this circuit? Well, charges start at the positive terminal, they exit, and they travel around toward the negative terminal. Where is this energy associated with the EMF? Where is it getting lost or converted? Well, there are 2 places you might look to. The first is the wire itself could heat up and convert some of that energy. In the other place, the resistor can heat up and convert some of that energy to other forms. We're going to pretend that we have ideal wires that don't convert any energy to heat. In other words, we're going to pretend that there's no resistance in the wire itself. Thus, all 15 joules per coulomb are lost across the resistor and converted into heat, or internal energy. So if we want to solve for I, the current, we know that the potential difference across the resistor is 15. We know the resistance of that resistor, and we can find the current passing through the resistor. Or in other words, we know V, we know R, let's find I. We would isolate I by taking V over R, and if we do 15 volts over 5 ohms, we get 3 amps, or 3 amperes. Not too bad, right? What if we have a case like this? Two ohms and 4 ohms. And this has, let's say, 24 volts of EMF. Well, this is actually pretty straightforward. We can take these two resistors and we can actually add their resistances together. And the reason is because there's only one path for charge to follow through both. If a positive charge comes out of this battery and it travels through the wire, it goes through one, it has to go through the other before it gets back to the negative terminal. When the resistors are back to back like this, we say they are in series. And we get the total series resistance by adding R1 plus R2, which would just give us 6 ohms in this case. On the other hand, we might have a scenario like this, where the charge could take a top path or maybe a bottom path. There are 2 different paths and the charges must choose. Some charge comes out and goes the top path and some follows the bottom, but when they get to here, they join back up again. In this scenario, let's say this is 2 ohms and this is 4 ohms. There's a different rule that we have to use. Because charge could go through this loop, or charge could go through this parallel loop, we say that this is a parallel circuit, or parallel resistors. And we don't add up 2 plus 4. That's wrong. In fact, that gives us totally the wrong result. Because consider, it's a lot easier now for charges to go around this circuit. You just opened up a second path, so some charges go this way through the top, and now other charges can follow this bottom path, and you've got more charge flowing, you've got less resistance on the whole, and you've made it easier by opening a second path. So the resistance we expect should go down when you add a second route. The way that we calculate that resistance is by adding the inverses. This is a weird equation, and if we have more, we keep going. But it works out. Let's practice with this problem. We have 1 over R total equals 1 over 2 ohms plus 1 over 4 ohms. And 1 over 2, that's the same as 2/4. So when we add, we get 3/4. But we're not finished. We have to flip both sides to solve for R total. And when we take the inverse of both sides, we get 4/3 ohms, or in decimal form, 1.3. And look at that. The total resistance is less compared to the individual resistances. And again, that's because if we only had one of these paths, now you're forcing all of the charges that were the ones that are going the top path, they still go the top path, but the ones that were going the bottom path, now they're being forced through this same tiny little section above. And now that would be higher resistance. By opening a second path, we expect the total resistance to drop and be less than 2. And that is exactly what we see in this answer.